Hello, everyone. Let's continue with our topic groups and subgroup. We are in section 3, isomorphic binary structures. And today we will answer the following question. How to show that binary structures are isomorphic? Well, in order to answer this question, first, let's recall that a binary algebraic structure is a set together with a binary operation. Also, we should recall the definition of isomorphic binary structures. And for this, I have already written the definition, and it says the following. Let S asterisk and S tilde asterisk tilde be binary algebraic structures. An isomorphism of S with S tilde is a one-to-one function phi mapping S onto S tilde such that phi of x asterisk y is equal to phi of x asterisk tilde phi of y for all x and y elements of S. This is known as the homomorphism property, and this notion of homomorphism we will see in some future videos. Also, we have the following. If such a map phi exists, we say that S and S tilde are isomorphic binary structures, which we denote like this, where we omit the binary operations. So, we can say that these two binary algebraic structures are isomorphic if there exists a map which is one-to-one onto and satisfying the homomorphism property. Okay, so now we give an outline showing how to proceed from the above definition to show that two binary structures S asterisk and S tilde asterisk tilde are isomorphic. So step 1 is, according to the definition, is define the function say phi that gives the isomorphism of S with S tilde. Second, we should show that phi is one-to-one, which is the same to say that phi is injective. And step 3, we should show that phi is onto S tilde, or which is the same to say that phi is surjective. And finally, we should show that phi of x asterisk y is equal to phi of x asterisk tilde phi of y for all x and y in S. Okay, so let's do now in an example. So let's see example. Show that the set of real numbers with the addition is isomorphic to the set of positive real numbers with multiplication. Okay, where plus and dot are the usual addition and multiplication. Okay, so as a step one, we should define a function, right? So observe that somehow we should convert the operation of addition to the operation of multiplication. And also, from this property, give us an idea how to do this. A to the x plus y is equal to a to the x multiplied by a to the y. So this tells us that addition of exponents corresponds to multiplication of two quantities. So we can try, defining phi from the set of real numbers to the set of positive real numbers by the following rule. Phi of x is equal to e to the x with x a real number. And here observe also the following. This is a positive in a real number. So in fact, this is a positive real number as we want, right? So step 2, we should show that this map is one-to-one or injective. So let's suppose that phi of x is equal to phi of y. Then, by definition of this map, this is the same. This is equal to the following. And then, taking the natural logarithm, we have the following. And this implies that x is equal to y. So this proves that phi is one-to-one. Okay, so now step 3. We should prove that phi is surjective. Okay, so if we take here a positive real number, then we know that natural logarithm of x is a real number. Okay, we found a real number. And we have the following. And observe that phi of this value is equal to this, which is equal to x. So we have already proved that surjective. Okay, as a step 4, we should prove that this phi satisfies the homomorphism property. So let x, y be two real numbers. We have the following. We have that phi of x plus y is by definition e to the x plus y. And by properties of exponent, this is e to the x multiplied by e to the y. And by definition, this is phi of x multiplied by phi of y. So by step 1, 2, 3, and 4, we conclude that phi is indeed, is indeed an isomorphism. Okay, similarly, let's see another example. Okay, so let 2 times C be the set of all even integers. Of course, positive, negative, and zero. Show that the set of integers with additions is isomorphic to the set of even integers with addition, where plus is the usual addition. Okay, so by step 1, we should define the function, right? So step 1, the obvious function to try is the following. Is phi going from C to the set of even integers given by P of n is equal to 2 times for n an integer. And step 2, we should show that this is injective. Okay, let's assume that phi of m is equal to phi of n. Then by definition, this is equal to the following. 2m is equal to n. Then this implies that m is equal to n. So phi is 1 to 1. And now we should show that in step 3, we should show that phi is surjective. So if we take n even integer, then n is equal to 2 times m for some m integer, and we know that this is equal to n divided by 2. Hence, phi of m by definition is 2 times m, and is equal to n. So phi is onto this set. And finally, we should show that let m and n, this map satisfies the homomorphism property. So then we have phi of m plus n by definition is equal to 2 times m plus n, and this is by properties 2 times m plus 2 times n, and by definition this is phi of m plus phi of n. So that phi is indeed an isomorphism.